Okay, there we go. So recently, 1,000 college seniors were asked whether they favored increasing their state's gasoline tax to generate more funds, to improve highways, and whether they favored increasing their state's alcohol tax to generate funds to improve public education system. So they're, being given these two options. So after the responses were tallied, we had the following results. We've got 746 students who favored increasing the gasoline tax, 602 that favored increasing alcohol tax, and 449 were in favor of increasing both taxes. So they want to know how many of these 1,000 students favored at least one of the taxes, how many favored increasing only the gasoline tax, and how many favored increasing only the alcohol tax, and how many favored neither. So you can see the questions they are asking us, those were not all answered from this tally over here. So you've got 746 who want to increase the gasoline tax, 602 who want to increase the alcohol tax, and 449 who want to include both taxes. So if you think about it, those 449 that are saying that they are okay with increasing both of the taxes, those people are actually being counted in your 746 and the 602, because this one is just talking about how many wanted gasoline and how many wanted alcohol taxes to be increased. But those who are going for both taxes, like I said, are included in both these categories. So when they ask you a question like how many only wanted the gasoline tax to increase or only the alcohol tax to increase, you have to do a calculation to find those numbers. How many wanted neither of the taxes to increase? Again, that information was not given to us, so we would need to calculate that. They also wanted to know how many were in the favor of increasing at least one of these taxes. So this is kind of where we get into our discussion of set theory and what a set is and how we can use these ideas to answer questions like this. So let's take a look at some definition over here. We're talking about a set being a collection of objects or things. These objects or things, in terms of jargon or terminology, are called elements, because they're members of the set, so we call them elements. So in this case, the example that we talked about with the students, showing their preference on tax increase, we can say the set is, based on these students, these 1,000 students, and basically who would favor, gasoline tax, who would favor increasing, not even increasing any of the taxes. Those are what we would call as our set of students. But again, your set can be depending on just anything you are working on. So as you can see, they're talking about a set can be all the state capitals, a set can be all the states, west of the Mississippi. So again, like I said, it just depends on what we are working on, what context we are talking about, and your set can be, like it said, a collection of objects or things. So they're saying, if we're talking about set of state capitals, then we can say Des Moines is an element of the state of capitals, right? Because it is the state capital of Iowa, whereas Dallas would not be part of that set because Dallas is not a state capital. So it just really depends on, what your set is and what those elements are going to be. Now, they are saying such sets are called well-defined because there is a way of determining if, that item is going to be an element of the set or not. So again, some terminology here is what is a set, what is an element, and what we would call as a well-defined set. So you've got some examples over here talking about, is it a well-defined set or not? So they're talking about, movies directed by Alfred Hitchcock, that would form a set. The set of all great rock and roll bands, the set of all possible two-person committees selected from a group of 5 people. So if you think about it, the set of all movies directed by Alfred Hitchcock, Now, obviously, if a movie was not directed by him, that would not become an element of this set. So only the movies that he has directed would go under this set. So yeah, we can say this is a well-defined set. But now, just when you look at the terminology, we're talking about the set of all great rock and roll bands. Now, if you remember, when we were talking about Logic and we had talked about having, oh man, that terminology just flew out of my head. Whether we had a statement or not, right? And we had talked about anything that is an opinion cannot be a statement, cannot be, cannot have a true or false value. So if you think about in those terms, when we're talking about a set of all great rock and roll bands, I may think one band is great, but you may say, no, I don't like their music. I don't think they are great. So this is what we would call as a not being a well-defined set, because this is a matter of opinion. So you can't really say a set of all great rock and roll bands. Now when we talk about the set of all possible two-person committees selected from a group of 5, well, yeah, because if you have a total of 5 people, and from those 5 people you're trying to create a committee with only 2 people, you can do different combinations and come up with what your 2-person committee would look like. So this is going to be, again, a well-defined set. So it really just comes down to, like they said over here, there is a way of determining for sure whether a particular item is an element of a set or not. Now, when we get into notations, again, we don't really want to write everything out. If we can avoid that by using kind of like we did symbolic logic, then it kind of helps us come up with certain notation. So again, what it means without having to write everything out in words. So a set is usually denoted by a capital letter. Okay, so if you wanted to give a title or a name to the set of all Alfred Hitchcock movies, we could call it capital A, capital M, whatever letter you wanted to use, as long as it's a capital letter. So they're saying, pick a letter that will frequently remind you of the contents of the set. So a notation that will, serve as a reminder. We are talking about roster notation, or, a listing notation. And this is where you take each of your elements, that fall inside the set, and you actually put it in these set of braces. So, curly brackets or whatever you want to call them. So these are called as set braces. And here's another thing that would probably be helpful. So just remember that when you are listing your elements in a set, you don't have to list repetition. Each distinct element is only listed once. And honestly, the order is not important. We're just used to putting things in order, but to put them in a set notation or roster notation, you don't have to put them in order, but just remember each element only needs to be listed once. So if there's a repetition, you don't have to write it multiple times. Another symbolism that we use here is to show that this is an element of. So it kind of, you can see, looks like an E, but it's not exactly an E. And this stands for is an element of. If you put a little line across that symbol E, that means this is not an element of. So again, just 2 symbols to show you if you're trying to show this, this value or this object or this thing is an element of set A, or this object is not an element of set A, then those would be the 2 symbols. Another terminology to be familiar with is the cardinal number. And this basically means how many elements are in the set. So cardinal number just means how many elements does a set have. And again, as a notation, we use small letter n, and the A stands for, whatever your set is called. So remember, we use capital letters for set. So this is kind of a neat example over here. They're using set R for the set of all letters that fall under the name of Ramones. So you can see they're using capital R because, again, it reminds you of the Ramones. And so Ramones, these are the letters that make up the word Ramon. So they are going to be the elements of this set. So you can see they are showing us that M is an element of R because you can see M is one of the members here, but X is not an element of R because, nowhere here do we have the letter X. So that's kind of how you use these two symbols for being an element of or not being an element of a given set. So remember, your cardinal number, N of A, in this case would become N of R because we're looking at the set of Ramones. And that, of course, you have 7 letters in there. So the cardinal number for the set of Ramones is going to be 7. So it's just how many elements does a set include. They're talking about 2 sets being equal. So this is, of course, where they would have the exact same elements, right? And again, remember the order in which the elements are listed is not important, as long as each of your elements will match, right? So they're talking about set M being, all the letters that make up the name Moners. So you can see this is what the roster notation would look like. And you can see, obviously, if you rearrange those letters, it forms the name Ramon. So we can say M is equal to the set R because they have the exact same elements between both those sets. Again, order is not important. And, we had talked about, if you, go back and think about chapter 1, we had talked about, 2 statements being equivalent or 2 sentences being equivalent if we did the truth table, right? And all the values came out to be true. So in this case, we're talking about as long as all the elements are the same, you've got, 2 sets being equal to each other. So now another thing to kind of keep in mind, these examples are very simple. I mean, you've got 7 letters in there and stuff like that, but it's not always going to be possible to describe, everything in a roster notation, because think about this. If they're talking about set V being all the registered voters in Detroit. And, if you think about the population of Detroit and how many people might be registered voters, that's going to be a pretty long list, right? So you cannot really use the set notation to write out everybody's name in there. Even with a computer program, it would still be a very, very long list. So you really don't want to write everything out. Some sets can contain an infinite number of elements. If there are an infinite number of elements, again, how are you going to list everything out? You can kind of think about, they're talking about set G as all the negative real numbers. And we know this is going to be an infinite set. So we wouldn't be able to use that. So the idea here is we actually end up using what we call as a set builder notation. So for our, set of all negative real numbers, you can actually write it out in this form over here. So what this is basically saying that X is an element of set G, where X is going to be less than 0, which means X is negative, and X is part of the real number set. So you can see they are saying X is an element of the real number set. So these 2 conditions actually tell us that we are looking at negative numbers because they're telling us X has to be less than 0, and we know X has to be a real number. So this is basically telling us set G stands for all negative real numbers. So that's kind of how they're defining this by using the set builder notation. For our registered voters in Detroit, this is actually how you can write it out using the set builder notation. So here, since we are talking about, people who are registered to vote, we can't really use this kind of symbolism that we did with set G. But here we can say our set V for voters is going to be people or persons. And these are, this is a person who is registered to vote in Detroit. So you're kind of having to write this out, but you can see this gives us a pretty good description of the people who will fall into this set V over here. And you can see how they are writing this out in words for both of these different sets we have used here. So you can use the set builder notation for, sets that are really, really large. If they are small enough, then you can use your roster notation like we did over here with the Ramones and the Moners. So it really just depends on what kind of set you end up working with. And then they've got, a couple examples here just to make sure you're able to understand how to read set builder notation. So here you can see, again, we have a set with element X, where X is a positive number and X is again part of the real number set. So that means you are looking at a set of X. So this is the first part, set of X, which is going to be the single X over here. And then this vertical line that you see, that's what you read as such that. So this is set of X such that X is a positive number and it's a real number also. So X is a positive real number. So that's kind of how you are reading the sentences or these set builder notations. For the second one, you have persons. So we can say the set of all people. Again, for this vertical line, you have such that the person is a living former US president. So that's going to be the second part. Same thing for set 3, it's a set of all women. So that's the set of all women for your vertical line, such that the woman is a former US president. So you can see, this is going to be an infinite set over here for the first one, because that is positive real numbers. And those numbers are going to keep growing and growing. As far as the former living US president, that set is going to be a finite set because, there's only a few living presidents left, right? So, this is not a very large set, but again, instead of using the roster notation, you can use the set builder notation also, like they show you over here. For the last one, the woman is a former US president, this set is going to be an empty set because obviously there's nobody, we've never had a woman US president, former or current, right? So that's going to be an empty set. And you can see that means its cardinal number is going to be 0. So a lot of times you have to be very careful about this number 0 because N of W, right? The cardinal number for the set of women US presidents is 0, but the number 0 itself can be an element of a set. So they're kind of trying to show you that distinction over here. A lot of times we also use this symbol, 0 with a slash through it to depict an empty set, or we use these empty set braces. So you can either use this or an empty set, where basically you're showing you've got the two braces, but there's nothing in the middle. All of these can be used as symbols for your empty set. However, if you have a set that actually has the 0 as an element, so trying to think of an example that would follow this. Nothing's really coming to mind, but basically we are saying you have a set and, we can call it set Z, and it only has one element in it, and that element happens to be the number 0. So when you talk about the cardinal number for set Z, remember there is one element in your set. So that's actually going to be a cardinal number of 1 and not 0. So it's a slight distinction between a set having a cardinal number of 0, because that means you have an empty set. But if you have a set that has the element, a member, which is the number 0, then that means the cardinal number for that set is actually going to be 1. So just a little bit of that difference between a cardinal number of 0 and actual element being the number 0. So the difference between the two. So this was just, your basic terminology with what is a set, the set builder roster notation, what's a cardinal number, um, and, of course, what is a well-defined set. So some terminologies to, get comfortable with. Now we're getting into a little bit more in depth with our definitions with sets and subsets. So when we talk about a universal set, we're basically saying a set of all possible elements of any set that can be used in the problem. So, your universal set will keep changing depending on the problem or the example you are looking at. So it's not always going to be, because it says the word universal doesn't mean it's going to stay the same for every example. Based on each example, the universal set will change. So right now we're using the example of, if we're talking about spelling words, then your set U can be the set of all the letters in the alphabet, right? So going all the way from A to Z. And then we can talk about if we were going to use, some of these letters to make up words, then those can be your subsets. So they're saying when every element of one set is also a member of another set, we say that the first set is a subset of the second one. So every element of one set, if it is going to be a member of another set, we say that the first set is a subset. So you can think about, there's a set that uses the letters PIN, and there is a set that uses the letters PINE. So you can see PIN are part of the PINE set. So that's why we are saying PIN is a subset of PINE, because, again, every element in one set is also a member of the other one. So we use A is a subset of B, or you use this notation. So it looks like A, and then it's kind of like a C shape with a line underneath that. A is a subset of B, and that of course means that every element of A has to be an element in B also. So, the PIN set, if you had, let's say, an S in there, but the PINE set does not have an S in there, then, of course, they would not be subsets. So everything that is in that smaller set or the subset, all of those elements have to be in your, bigger set or the second set that you're comparing it with. They are also saying, alternatively, A is a subset of B if A contains no elements that are not in B. And that's kind of what I was saying, if PIN had an S, but PINE does not have an S, then they would not be subsets. Or, A would not be a subset of B. So they're saying no elements that are in A, A must not contain any elements that are not in B to be a subset. If A contains an element that is not in B, then like I said, A is not a subset of B, and this is the symbol you use. This is where you just put a slash through the symbol and A is not a subset of B. So it's kind of like you're canceling it out, right? When you put that little slash through it. So you can see again, more examples over here talking about countries that are permanent. They have a permanent seat on the UN Security Council, and they wanted to determine whether the given set is a subset of P or not. So, in this case, of course, then you would need to know what countries are, what countries have a permanent seat on the UN Security Council. And then based on that, you can come up with your examples. So the first one is asking us to determine whether set A is a subset of set P or not, which is the Russian Federation and United States. And you can see, if you just list all the elements from set P, these are all the countries that have a permanent seat on the UN Security Council. So obviously you can see both Russian Federation and United States have a permanent seat in the UN Security Council. So we can say, yes, A is a subset of P. For the second one, you've got China and Japan, So you can see, of course, China has a permanent seed, but Japan does not. So since there is one element in this set that is not in your original set P, that means set B is not a subset of set P. Okay. The next one is asking us for set C, which is United States, France, United Kingdom, China, Russian Federation. And if you compare all 5 of these countries, you will see all of them are listed in the original set P. So in this case, every element of set P is also, sorry, set C is an element of set P. So technically, they are equivalent sets, right? C is equal to P. So in this case, it actually means C is a subset of P, and it actually also works in reverse. P is a subset of C. So if they're equal to each other, guys, they can actually be each other's subsets. So it works in both directions. C is a subset of P, and P is a subset of C. And this is only when your 2 sets are going to be equal to each other. So they're saying every set is a subset of itself. So you can also say, P is a subset of P technically. And then the last one is an empty set. There's no elements in there. So since set D is an empty set, technically it can be a subset of the original set P. So even if it is an empty set is a subset of all sets. So that's kind of like one of those default things. An empty set will be a subset of no matter what your original set is going to be. So just again, some little discussion on subsets. So what I wanted to do was just do a basic example over here. Just to get you guys, a little bit of practice with sets and subsets before we get into our Venn diagrams. And we did a little bit of, Venn diagrams when we were talking about logic, but we didn't get, technical with our discussion. So let's take a look at some example over here. Okay, so we're just getting into section 2.1 and let's look at okay, let's do number 6 over here. So here are your instructions for number 6. Okay, so they're telling us list all the subsets, identify which sets are proper and which are improper. So we haven't talked about that. We'll talk about that in a minute, but let's talk about all the subsets for number 6 over here. So we're trying to create subsets. You can see it's a music category. So they've got classical, country, jazz, and rock. So you're trying to create subsets from them. Take a minute, think about it. Let me see what your answers come out to be, and then we'll discuss if you were on the right path or not. So just, have your answers ready. Don't send it just yet. And you don't have to give them names, just use your braces and then, whatever you want to put inside of it. If you're doing multiple ones, then just use a comma to separate your subsets and, whatever you want to write inside of it. Because remember, you can have multiple subsets. There's not a rule that you should only have one or, anything like that. So classical, country, jazz, rock. Those are the four elements of the original set M. And what will your subsets look like? So take another 30 seconds, guys, and then we'll start sharing answers. Okay, go ahead, send your answers in. Okay. Oh, Logan, we're working on number 6. I think you went with number 3.
Whoops.
That's okay. Okay, Riley, I can see yours. You did classical, country, jazz. Okay, Idali, classical, country, jazz, rock. Okay, you're doing that as one set. Riley, you did yours in different ones. Okay, Riley got it. Okay, so while you guys are sending me your answers, let me open up my notebook page over here. Okay, let's see what else you guys came up with. Okay, Brendan, you're doing classical, country, jazz, and rock is all different sets, okay? Okay, Cynthia, same thing. Roman, okay, individually. Ashley, individually, okay? And you know, even though Logan had the wrong set, I don't know if you guys saw her answer or not, she also included the empty set as part of her, because you know, we just talked about that, that an empty set is a subset of all sets, right? So you can actually include an empty set as a subset, and then looks like most of you went with each individual word. So that's classical, country, rock, jazz. But you can also have, you know, more than one element, obviously. So you can do a combination of twos. So you can then do, let's say, classical with country, 2 elements in one set. You can do classical with rock. You can do, you know, classical with jazz. And those are also going to be subsets of your original set. For that matter, now that we've done a combination of classical with all the other 3 groups, you can now do country. We've already got country and classical, you know, as a pairing done. So now we can do country with rock, right? Then we can do country. What happened? There we go. We can do country with jazz. So there's actually a pretty big list of what your subsets would look like. So we've got country with rock, country with jazz. So that takes care of this. We've got rock with classical. We've got rock with country. So that would be rock and jazz together. So that takes care of the rock group. And then let's see, we've got jazz with rock, jazz with country, and jazz with classical. So that actually takes care of all your 2-element groupings. And then we can build into 3 elements into these subsets. So classical, country, and rock. We can do classical, country, and jazz. Let's see. So we've got classical, country, and rock. Classical, country, and jazz. What else can we do? Leave the country out. Classical, rock, and jazz. And then maybe leave the classical out and do country, rock, and jazz. So that should be our 3-element groupings. Can we do any other combination there? I think we covered all 3 elements. And then remember what we said, a set can be its own subset. So that means classical, country, rock, and jazz, all 4 elements can be a subset. So just look at that list. It really comes down to, every possible combination that you can think of is going to be a subset. So you can see just out of those 4 elements, how many subsets do we have over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different subsets. So that's just, out of 4 elements. So just think about some of these elements that have, like voters in the city of Detroit, how large those groups can be. So that is something, to keep in mind as you go through these examples of coming up with your subsets. Okay, so before we get into the Venn diagram part, I did want to talk about what is an proper and what is an improper subset. So you can see we are saying if you have a set which is equal to another set, so set A equal to set B, which means every element of set A is also an element of set B, or vice versa. This is where we say set A is an improper subset of B, or obviously in the other direction, B is an improper subset of A. So in our example that we just did over here, this last one that we looked at, the classical, country, rock, and jazz, where all 4 of these are together, this guy here would be an improper subset, because all the elements that are in this set are also in our original set, right? So that's your improper subset. For your definition for proper subsets, we're basically saying if A is a subset of B and B contains an element that is not in A, which means set B has more elements than set A does, they are not equal to each other, that is when we say A is a proper subset of B, because obviously we are saying set A has less elements than set B, and A has smaller number of elements than set B. So that's a proper subset. So in our example, that would be all the remaining subsets that we came up with, because you can see we stopped at a combination of 3 elements, right? So all 4 of our elements are not going to be, at the same time in these subsets. So all of these subsets, and I'm trying to find a different color. So all of these going from here all the way to here. All of these are proper subsets.
So the only way it's improper is if it has every single element?
Yeah, very good, Logan. Exactly. So it's basically equal to the original set to be an improper subset. And obviously remember, they don't have to be in the same order. As long as all the elements match, and like I said, the 2 sets are equal to each other, that's when you have an improper subset. But if you have a smaller subset where you don't have all the elements of the original set, that's when you're looking at a proper subset. So just a little bit of a distinction, when you are looking at these subsets over here. And I think you will see homework examples where they will ask you to identify your proper and improper subsets. And Venn diagram wise, as you can see, if you are going to be a subset of the original set, so what we do is we use the rectangle to show our universal set. So, if this was the example of all the alphabets that are used to, make words, then that would be your universal set. And then set B, you can kind of think of this as being our set M, where we were doing the classical, country, jazz, and rock. So you can think of all of those being, our subset, our main set over here. And then any of those proper subsets, or for that matter, improper subsets will be inside of that. So the smaller one on the inside represents your subset. The outer circle represents, the main set. And then the rectangle is, of course, for your universal set. So this is how we actually use Venn diagrams to represent visually the sets that you are looking at. Of course, you're not going to list all your elements or anything like that in the Venn diagrams. You're just using the rectangle and the circles just to kind of show what type of sets and subsets you are looking at. We'll get a little bit more into Venn diagrams when we go into our next section. Here, we're focusing more on just introducing you to the concept of sets, the different terminologies that we looked at. So kind of tying this, what we did with our logic. So you remember how we use the and connective word to make our compound statements? So think of the intersection of sets kind of being on that same line of and. And you will see that we actually do use the word and here to connect our two different sets. So when we're talking about intersection of sets, we're saying there might be an element in one set, which is also an element in another set, right? So we're saying your sets may overlap a little bit. They don't have to overlap completely. There could be some elements in the first set and some elements in the second set, which are the same. So this overlap is what we call as an intersection of sets. We're saying if an element is in two sets at the same time, that's an intersection of sets. So we use this, I kind of call it like an N, but it's an upside down N, an N, or you can think of it as an upside down U, however you want to think of this symbol as, or think of it as, how we used this symbol in our logic for and. Well, basically, instead of, giving you a V shape, it's kind of like an upside down U. And that means the intersection means that whatever element X you have in that set, it's gotta be part of set A and it's gotta be a part of set B. And you can see, again, we're using that word and to combine the two together. So we're saying whatever element is inside this intersection, it's gotta be in both your sets. Otherwise, it cannot be part of the intersection. So this was kind of a funny example they had in your textbook. So they're talking about set A is Aquaman, Batman, Flash, Superman, Wonder Woman. So they're defining set B as Batman, Blue Beetle, Booster. What am I missing there? Well, something, Booster something, Fire and Flash. So if you look at the two sets, A and B, of course, you will see that Batman is in both sets and Flash is in both sets. So that's what your intersection will look like. So just Batman and Flash are the ones that are similar between the two sets. But you can see there are some elements in B and some elements in A which are not same. So the intersection only carries what's common between the two sets. So remember, as they said, it's got to be an element of set A and it's got to be an element of set B to be considered in the intersection. And a Venn diagram, if we use the Venn diagram, this is how we represent that. So you've got elements in set A which were not in set B, right? So those are going to be here on the outside, and the intersection represents what is common. So, this is where your Batman and Flash would fall, is in this little intersection area. So this is how we use, Venn diagrams to represent our intersections over here. All righty, let's see. Another set of terminology is what we mean by mutually exclusive sets. So sometimes they're saying, a pair may have no overlap. So there's nothing common between your two sets that you are looking at. And here they're using an ordinary deck of playing cards to show us an example. So set D contains a card that is a diamond, and set S contains the cards that are a spade. So, if you think about a deck of cards, well, obviously, if the suit, the card is going to be in the suit of diamonds, or it's going to be a suit of spade, there's going to be no overlap. And so in that case, it means that no cards are going to be diamonds and spades at the same time. So your intersection is actually going to be an empty set, which means, as you can see, we cannot do this kind of overlap in our Venn diagram. It would actually end up looking something like this, because you're basically saying the two sets are separate. There's no overlap. So, there's going to be no common area in that. So that's why your intersection is going to be an empty set. And this is what we mean by mutually exclusive, or some textbooks actually like to call them as disjoint sets, because, obviously they're not joined together, they're separated, they're disjoint or mutually exclusive. So nothing common between the two sets at all. So we've talked about intersection, which, like I said, you can think of that as being the and from our logic statements. Your union, you want to think of it as the disjunction, or, the or that we were using in logic again. So it kind of follows in that same idea. Your element can be in set A, or it can be set B. It does not have to be in both of them. It can be in both, but if it's not, it still falls under that union. So they're basically saying the word or is really the most important part about your union over here. So the union of two sets is going to be a new set formed by joining two sets together. So that's basically, the union of the states. They're comparing it to, union of the states joining all our 50 states together to form our country, our nation. So in that same way, they're saying or is going to be the important part over here. And this means, and again, look at that. It kind of looks like, your disjunction symbol, just more like a U instead of a V. So A union B means your element X can either be in set A or it can be in set B. So it's talking about consisting all the elements that are either in A or B, or they can be in both, but that's really not necessary. As long as they're saying it's going to be in one of the sets. So, they've got another example over here. It looks like I don't know why I'm missing letters in here. This is so weird. And I think that should be a G. So they're saying set A is Daryl, Glenn, and Rick. Set B is Maggie and Michonne. So their union. And you can see, if you just look at the two sets, original sets, Daryl, Glenn, Rick, Maggie, Michonne, right? There's no overlap between either of those sets. So as far as the intersection goes, the intersection is going to be an empty set, because, these are mutually exclusive sets. There's nothing in common between these sets. But look at the union when we combine these two, because they told us the element can be in the first set or the second set. When I make a union, all of them are combined together. So now you've got Daryl, Glenn, Michonne, Maggie, Rick, all of them put together. And that's what makes it a union. But you can see our intersection was an empty set. So this is really the interesting part of how, union of sets work. And I don't know if you guys need to take like an algebra course anytime later in your study. but we actually use this idea of union and intersection of sets when we are defining solutions to equations, especially something like second degree polynomials, right? Quadratics and stuff like that. Okay, a lot of times we actually use this in what we call as interval notation. So a lot of times in algebra course, and I don't know if you guys had to take basic algebra or intermediate algebra, but if you had, then this is probably something you have come across in those classes. So this is where it comes from this idea of intersection and union of sets. So just to show you what the union Venn diagrams would look like, if you have mutually exclusive sets, which is what we have here, you know, with this example of Daryl, Glenn, Rick, Maggie, Michonne, even though they are two completely separate or disjoint sets, you know, these are mutually exclusive sets, but in the union, you know, we would be taking every element from A and every element from B and putting it all together. Now, if they were not mutually exclusive sets, which means there was something common between them, then this is what your Venn diagrams would end up looking like. So you've got set A, set B, and then whatever is common between both the sets. So just two different representations of what the union of your sets would end up looking like if they were mutually exclusive or non-mutually exclusive. Well, I'll wait for that in a minute, but questions on intersection and union of sets. Okay, let's do an example very quickly just to make sure everybody's comfortable with that. Let's do number 10 over here. So with number 10, they're actually giving you this as your universal set. So they're saying the universal set is set U going from 0 to 9, right? So all 10 of those digits are forming our universal set. And then number 10 is talking about set A being 3, 6, 9, set B 4, 8, and they're asking us to find the following. So let's do these A and B parts first. We'll need to come back and talk about C and D. So they're asking us to find the intersection and the union. So go ahead, get your answers ready in the chat. You know, write down what you think part 1, part A should be in part B. And again, just use your braces and just use a comma. So make the first one the answer for A and the second one the answer for B, and you know, then whatever you want to put on the inside. So intersection between sets A and B and union between sets A and B. So just get your answers ready. Don't send them just yet. Just make sure you have your answers ready. All right, go ahead and send your answers in. So intersection and union. So Idali, you actually want to put them as one single set, right? You don't want to do the first set union, second set. You put all the elements together, kind of like you saw in that Glenn Maggie example. So you will see how when they did the union, they put all of it together. That's how you do the union. There you go. And you have an empty set for part A.
Yes.
Alrighty, so let's take a look at this. Okay, Riley. Okay, so you've got 3, 6, and 9. You've got 4 and 8. So obviously you can see there's no overlap between set A and set B. So yeah, that actually tells you set A is an empty set, or of course you cannot put this symbol in chat. I'm not sure which one your homework will ask you to do, if it's going to do the empty set braces or if it's going to do the, the empty set symbol. But that's exactly what's happening, because these are mutually exclusive sets. And so there is no overlap happening between them. And then A union B, even if they are not anything in common, you can still combine them. So you can put them 3, 6, 9, 4, 8. Of course, order is not important, but if you wanted to, this is kind of what it would look like in order. But as long as you have all the elements from set A and set B together, that forms your union. And then, of course, your intersection is an empty set. All right, Nicholas, I see your answer in there also. Very nice. So a lot of you did not answer. Does that make sense to see what the answer for the 2 parts was?
Yeah.
Yeah, okay.
That helps a little bit, yeah.
Yeah, okay. All right, and we'll do more examples here. This was just kind of our first starting example. Let's clear this guy out and let's talk about those other symbols in there. So you've got a couple more examples here if you wanted to compare your answers with. Very quickly, you can see between the 2 sets, we have 2 that is in common. So when you do the intersection, you will see the intersection will only have 1 element, because that's the only element that's common between the 2. But when you do the union in this case, you will see again, guys, since that 2 is overlapping, you don't have to list it twice. You only list it once. So be careful when you do come across sets where you have common elements in both of them. Don't list them twice. Just once is enough. And then, of course, the intersection will obviously only have that 1 element in there too. And you can see how they are showing you with the elements. So you've got 1, 2, 3 in set A, and you've got 2, 4, 6 in set B. So 1 and 3 and 4 and 6 are on the outside. And in the overlap is where you have 2, because that's the number which is common between both the sets. So that's the only number that goes in the intersection. Everything else will be on the outside. Cardinal numbers. So remember, cardinal numbers is how many total elements you have in a set, obviously without repetition, just the unique numbers themselves. So they're actually showing you how to do the cardinal numbers calculation for union and intersection of sets. So that means you take each cardinal number for each original set, right? So for set A and set B. However, because the intersection means there's overlap between the 2 sets, you subtract the number that is being overlapped. So think about this. If we use this example over here, set A has 1, 2, and 3. So set A has a cardinal, come on, buddy, has a cardinal number of 3, right? Because you've got 3 elements here. Set B has a cardinal number of 3 also. So if I just add NA and NB, that would be a total of 6. However, if we talk about the intersection has only 1 element in it. If you look at the union has only 5 in it. So if I just add the cardinal numbers for A and B, I get a total of 6. But when you are calculating the cardinal number for your union, we would have, just using those examples, you would have 3 plus 3, which would be 6. But then our intersection, remember, only had one element. So that's why you subtract 1 from it. And this gives you the total for your union. So that's kind of where you have to think about, I am subtracting whatever is overlapping between the two sets, because otherwise what's happening is this number 2 is being counted once with set A and it's being counted again with set B. So you're actually calculating one number twice and your calculations would be incorrect. And that's why we subtract the cardinal number from our intersection to get this. And you can reverse this formula to get the number of intersection by itself, and your union would move to the other side. So this is just like solving an equation that you would do in an algebra-based class. And they're showing you some examples over here again to kind of help you with those cardinal number calculations. So you can kind of look through these examples here. So this notation is what I wanted to talk about, with the little, oh man, again, that word kind of went out of my head. Yeah, I guess prime, A prime. So when we talk about the complement of a set, we're using this notation of A prime, or you can basically say the complement of a set. This is basically talking about elements that would be in your universal set, but not be in set A. So when it's A complement or the complement of set A, we're saying basically every element that is not in set A, but it's in the universal set. So if we come back to this example over here, yeah, Cynthia, we're almost done over here. So just when we're talking about complement of set A and set B, remember your universal set here is all the digits going from 0 to 9. So when we're basically saying the complement of set A and set B over here, we're basically saying anything that is in the universal set as long as it's not in set A. So for your complement of set A, this would be 0, 1, 2, we cannot use 3, 4, 5, we cannot use 6, 7, 8, and we cannot use 9. So everything that you had in your universal set except what's in set A. So obviously in that same way, it's going to be the complement of set B. So since this is 4 and 8, that means we can do 0, 1, 2, 3. We cannot use 4. 5, 6, 7. We cannot use 8. And then 9. And this is what your complement of set B will end up looking like. So basically, guys, whatever is in the universal set, but it's not in set A, is the complement of set A. Whatever is in the universal set, but it's not in set B, becomes the complement of set B. So it's almost like, you're subtracting what's in the original sets A and B and just leaving behind everything else from your universal set. So that's kind of how the complement of your set works out to be. All right, guys, so I wanted to get this done so that way you can at least get started on your 2.1 homework. And then, of course, if you have any questions, let me know, and we will continue with this discussion on Friday. So I know, Cynthia, you said you had to leave. So if you have any questions, send me an email. But if the rest of you want to stay and ask me questions, that's fine. And if not, then I will see you on Friday morning. All right, guys, have a wonderful day. Be careful. Take care, everyone. Be safe.